This is just a brief overview of how to use OpenProp. I show you OpenProp's website here. Just Google OpenProp, it comes up. It is freeware. It is a propeller and slash turbine design code. It uses lifting line theory to solve for the forces on a turbine, and then includes some, in addition to that, some viscous approximations, because lifting line theory is an inviscid theory. It's very well written and pretty well documented, and it's free. So you can do a lot of design work with it. You can design propellers. You can do parameter studies with this. We're just going to use it to solve for the performance of a single propeller. We're going to specify the geometry. So let me close this page here. Alright, so first thing you do is download the zip file from the website, and then put it in your MATLAB folder, and then find your way to that folder. Let's see, I think I have my Dropbox courses. 490 16. Okay, I have it in here in OpenProp. So now my working directory is in this OpenProp directory. There's only one executable MATLAB in there, which is openprop.m. The rest of the stuff, examples, are example setup files. We're going to do everything through the GUI. Now, to really use the power of the program, it's better to use the MATLAB files, set up your own input files in your input deck, but we'll use the GUI to simplify things. So I'm going to run that. Okay, so this brings up the OpenProp interface right here. You are to calculate some parameters for a propeller. I'm just going to put some in here for fun. So I'm going to put 4 blades. The rotation speed, this is not N in class. N is rotations per second. This is RPM. So if I wanted 2 rotations a second, that's 120 RPM. I'm going to put a 4-meter diameter turbine in there. For thrust, let's just put on 300,000 newtons or 300 kilonewtons. Ship speed, 5 is good enough. And hub diameter. Now for hub diameter, I'm asking you to sort of compare with the prior problem in the homework, which uses the wagon engine propellers. I think the beef, I can't remember which one I asked you to use, but anyway, they specify in figure 16.2 in your book, it shows you the profile of that series, and their hub diameters are about 17% of the rotor diameter for the whole series. So actually I could use MATLAB to compute that, couldn't I? Anyway, I like to use Python. So 17% is going to be a 4, so that's 0.68. So I use 0.68 meters for my hub diameter. And we'll go seawater. Okay, you don't have to change the paneling. This should be sufficient. This is for you. For those of you who use Tornado in the aerodynamics class, this is the same concept, where you're covering the. I dropped the website, but you're covering the propeller in these panels, and each of these panels is basically a vortex source, and it creates vorticity, and then you're matching boundary conditions to keep the flow parallel to these blades, and doing some funky stuff with the wake in order to figure out the strength of that distribution, which ultimately sets up the pressure distribution, and therefore lift, induced drag, etc. on each of these blades. As I said, it's an inviscid program, so the viscous component, so you have some drag on the blades, which leads to the part of the requirement of torque or horsepower due to the induced drag, and you also have, of course, viscous drag, which is approximated in there. And here's the blade design variable. So this is where you are in the blade. You're at 20% of the way out, 30%, 40%, 50%, all the way to 100% of the way out. C over D is the chord. Now this is the total chord, not the projected chord. Excuse me, of each of the blades, and it's written in terms of the diameter. So this is for a single blade of our 4. You can see its thickest around here, where it reaches about a quarter of the diameter of the propeller, and then thins back out. And then the last point I don't think can be exactly 0. I suspect that will blow up the program, but I'm not sure. So you want to keep this a small number. So if you wanted to affect the distribution of the chord lengths or make the whole blade wider, essentially increase the blade area ratio, you could increase all these numbers by some fraction, for example. That would be one smooth way to do it. This is a drag coefficient. Normally what you might do is take the section characteristics, which are selected over here, and get a sense of at the blade Reynolds number, or maybe at an average blade Reynolds number, perhaps one based on 70%. The velocity experienced by the blade section about 70% from the hub to get a Reynolds number, to get a drag coefficient. Alternatively, you can compute individual Reynolds number for each of these blades. Basically, as you get further away, the Reynolds number is going to increase, and come up with some X-flow approximations. We're going to stick with these constant drag coefficients here. And this is a thickness distribution. I'll show you the thickness profile, but basically this is the thickness relative to diameter of the section. So if you were to saw the blade off here or here further from the hub or further from the hub and measure the thickness of the section that makes up the blade at that point, you would see this. And you can see it's getting thinner. In fact, it rapidly thins and then it sort of stays the same here. They do have a 0 thickness tip, which is interesting because they have a non-zero thickness chord. So I'm not sure about the numerical properties. Sometimes things go funky if you make things 0. And skewness, as we'll talk about in class, is primarily used to reduce vibrations of the propellers, essentially sweeping them back, curving them around, more like a scimitar shape. We'll leave this 0 because the propeller series that we're comparing this to does not have skew or rake. So we'll leave that as is. Now, for the speed here, it will mention this in your homework, use the advance velocity of the propeller. So we'll pretend we're doing an open water test. There is no wake, but it's open water test at the advance velocity, not at the ship speed. Otherwise, we could put the ship speed here and then have to mess with the advance velocity, basically the wake defect, which you can specify as a function of radius, which is quite interesting. You can have a rather complicated wake shape if you want to here, and it will design the blades to deal with that. We're not going to do that. We're going to assume a uniform profile, uniformly slowed down by the wake factor to be slower than the ship speed. So use, where it says ship speed here, I'll say the homework, use advance velocity. Leave this blank. If you leave this blank, it assumes the wake is 0 and that there's no azimuthal, or circumferential, I should say, velocity field either. So it'll basically fill these values in with very simple values. Put performance curve on. If you leave this off, let me say, if I take this off and I run this program, essentially what it's going to do is going to specify, this specifies the geometry. This is the section characteristics. This is the diameter. This is the hub diameter. This is the thickness distribution. And these specify the airfoils. The camber and the thickness distribution are specified with these two. There isn't a lot of variation in the options they have here, so I wouldn't mess with these. And so that basically sets up the geometry except for twist, except for the pitch variation of the individual components. And what this will do, the program will do, is pitch the blade, essentially pitch the blade until it reaches a pitch angle at which it can produce this thrust coefficient, which is 0.028. That seems very small. I must have missed a 0. Hang on. Okay, that's better. 0.28 at a advance ratio of 0.625. So just like we'll do in class, we're going to do the same thing in the book. We're going to be computing J, computing KT, figuring out from a particular propeller series which pitch diameter ratio creates this at this advance velocity, or which is the closest one, I should say. And then based on that propeller at this advance ratio, we can get the efficiency. That's the propulsive or efficiency of the propeller, the open water efficiency. So this will do kind of that same thing in a sense. It's varying the pitch of the propeller until it reaches, that propeller can produce this KT, basically this thrust, at this forward speed in the non-dimensional sense. So I'm going to leave this default propeller. It's going to create a directory called default propeller. If you want to change this, that's okay, but just know it's default propeller. Let me run this. Let me just double check everything real quickly. Okay, and I am going to select performance curve. So what it will do is not only calculate the P over D and give me the efficiency of the propeller in this state, it will also take that same propeller and run it for a variety of advance ratios to get the KT, to make a KT KQ curve versus J, and it will show you where your design point is in that curve, which is helpful to see if, for example, you've picked the right diameter propeller, whether it's too highly loaded or not loaded enough, for example, or maybe you need a different blade area ratio. Now, the true design capability of this code can take into account cavitation. Essentially, you put in lift coefficient restrictions, on the blade, maybe as a function of radius from the hub, but you could just think in simple terms, a constant lift coefficient restriction, just like you did for your hydrofoil optimization problem, where you determine that CL, the max CL, basically your CP min gave you what the max lift coefficient is you could achieve before cavitation, and then you had to adjust the surface area of your hydrofoil in order to achieve the desired lift. In this case, I totally forgot what I was saying. Oh, so this program can do the same. It can bring in that CL constraint, and that CL constraint essentially does the same thing. Now what we can do here is if we find we're in a situation where we're running into cavitation constraints, we can increase the blade area ratio just like you increased your planform, thus decreasing the overall lift coefficient needed to be achieved by these blades to produce the same thrust, completely analogous to your hydrofoil problem. But this OpenProp can do a lot that's described in the web page, and documentation comes with a zip file that is in one of the subdirectories, which I'll show you. So let me run it. Oops. Okay, so it's creating graphical text reports. So that was for the design point. Now it's running each of the advance ratio points. Running. I'll let it run all the way before we have a look at the result. Okay. The result pops up right away because this is for the design condition before it runs the performance curves. So I let it run to the end. It's done. I'll leave everything in SI units. Okay, so there's J, there's KT. Those are properties of, essentially, our input values are going to set these. Here's the KQ, resulting KQ at the J in KT. Of course, KQ is the torque coefficient. That torque comes from the blade drag, in a sense, largely in the sense the induced drag and the force, as well as the lift force in the torque direction and viscous drag. So those come together to create this. So it's a little bit, but not super sensitive to those drag coefficients because these props aren't super high aspect ratios. So there are other sources of drag. So that 0.008 is fine. And this is your efficiency, FE, efficiency. The same as eta naught that we'll be computing in class, about 6.6%, not percent, 0.6 is your efficiency. Now, we can investigate, so that's a good number to remember. Now, you can always come back to that. This is on the design performance menu of the output. Let's just have a look at some of the things that we have here. Okay, I will start, I guess, with the 3D geometry. So click on that, and it'll show you the 3D geometry of the plot. This is up here is your 3D zoom in MATLAB. It's a 4-bladed prop, which we can see here. I'm not sure how you tell which fore and aft because these blades are pretty symmetrical. There's probably some convention from marine hydrodynamics to this green and red, but I don't know what it is. I don't see a difference. Now if we look at the sections, you'll see some difference between the leading and trailing edges, but it's pretty small. Anyway, you can zoom this around, and if you were to change the number of blades or change the, for example, the distribution of the area on the blades, you would see that here. So it's a very smooth distribution. Now this distribution of area, expanded area, comes from the chord, which is again the expanded value. It's the curve value that you set, or that is what came preset in the geometry menu. That was the root value, or the value at like 20%, 30%, 40%, 50%. It was thickest around here, and then decreased to 0.001 up here as a fraction of diameter. And it puts in some kind of standard hub here. And again, this hub diameter was part of our input. 2D geometry, we can see the sectional shapes here. This is at the root, very thick. Oh, actually, let me skip, sorry, to one thing. I want to show you blade thickness first. This plot is not to scale, obviously, but this is the thickness of each blade element versus distance from the axis of rotation in r over r. So in distance coordinate divided by the radius. So it ends up at 1. You can see it's thickest, of course, at the root. The profile is pretty linear, and then it just goes to 0 at the end. I don't see a lot of fancy variation in this. But of course, bending moment decreases linearly. Actually, that's not necessarily true. It depends on the loading of the propeller, I suppose. But if the propeller is constantly loaded, then you would want a linear thickness distribution if bending moment was in fact your enemy. Of course, construction costs are a part. Anyway, so that's a thickness distribution. That is also came from the input. That basically you see right here, 0.0329 down to 0, and that's what you're seeing here, time to 0. So that's this. Let me go back then to the 2D geometry. So you can see this red section. That's the very first section of the propeller, stretching out to the, not the very last, but almost very last section, possibly very last, I'm not sure in their paneling, of the, you can see how thin this last blade is, and you can see both how the thickness is varying in the propeller, and you can see how the angle of attack, the relative pitch angle, is also varying with the propeller. So this is the X direction right here, and you can see how as the blades get further from the hub, so that they're moving faster, and the rotation, the component of velocity that's due to the rotation is higher, they tend to be pitched down. So it's rotating essentially in this plane right here. So this blade is moving here to the right. This black blade is moving to the right, producing a net lift force that's in this direction right here. So it's partially, so if I put a lift vector on here, it points mostly in the direction of wanting to travel, a thrust direction which is up the screen, and a little bit to the left, which is counter to the direction it's rotating, which is basically like a drag term in terms of the torque. So you can see how that variation occurs here, and really how very important these last components are. So it is quite striking, the thickness distribution variation in this propeller. I don't think you see quite this drastic a change in things like wind turbines, propellers, because the forces at play are pretty significant, have this big thickness variation. You can see it's a cambered profile. It's a slightly cambered profile. Here's the mean. Here's the chord here. So it's cambered. This is the suction side. This is the suction side. A little bit of camber to it. The bottom is pretty flat. This is pretty typical of a propeller. The bottom side is fairly flat compared to the suction side, and it's a bit of an odd-looking airfoil. And the trailing edges are pretty close to being sharp. Depends how this vorticity is treated here. But very nice looking. You can look at other stuff. For example, we looked at blade thickness. Now this is the expanded blade. So this is the area if you unwrapped the propeller, or basically cut the blade off and hammered it flat on your desk. I guess that's what you would result in, this expanded blade area right here. So it's not the same as projected. And if you take this area, basically roughly 0.8, multiply that by r, and that gives you, which is 2 meters, and that gives you a length in real meters here, times roughly the average distance here is about 0.4, minus 0.2 to 0.2. So 0.4 non-dimensional coordinates, multiply that by r, and you get a real distance here. So that's 0.8 times 0.8 times 2 times 4 blades, and that will give you roughly the total area that the blades are, and you can divide that by the total area of the propeller, which is just pi r squared, and that will give you blade area ratio for this. And so for the propeller series we're looking at, they're 0.4, 0.6, 0.7, somewhere like there. The higher area ratio is about 0.7. I haven't looked at some of these other ones. You can have a look at these: induced velocity, circulation distribution, and link these back to our talk about lift. But I won't ask you to do that. So the key thing of this, and then we'll go to the performance curve. This is J, advance ratio, and this is KT, and the usual presentation: KT blue, 10 KQ in red, and then you have the efficiency in green. Which is this curve right here, peaking out here near advance ratio of 1. Our particular design point is right here. Our advance ratio, if I click back for 1 second, 0.625, KT was 0.285, 0.65/0.285 is this point right here, if you can see my cursor. And so this propeller at this particular P over D is producing this KT at this J, which is what we've asked it to do, and the efficiency there is basically 0.6, a little above 0.6. If I go back to design performance, 0.6. So it's a beautiful classic KT KQ curve coming from simulation. It's very nicely done. Now I'm not sure if these individual dots represent their points. It would be a little strange to me because they seem to run a lot of points where things aren't really happening and not so many points where things are happening, but who knows. So that's basically the gist of it. The one other thing I want to show you is that it was not clear to me how to get at what the pitch of this propeller is, but you can open a file to see what that is. So let me grab this terminal. I'm just going to grab my directory where I'm in here and CD to that directory. Okay, so let me go up one. So if I open a Finder, okay, I'll do this as real humans from this century do. They use Finder. So how to use Finder? This is so sad. MATLAB. Okay, and then, all right, so this is the directory structure. Again, this OpenProp is the code we ran from MATLAB. It created here a default propeller, 315. This looks like what we did. Now, this file right here, geometry.txt, open that with a text editor. I'm not sure what's about to happen. Okay, open with TextEdit in my Mac, and you see the actual geometry. Here's R over R. This is a geometric coordinate, non-dimensionalized, away from the axis of rotation. Here's the chord. These parameters were user input, thickness, user input. The key one we're looking for here is P over D. There's a slight variation of P over D, and again, it is pitching the propeller, but it's pitching each of the individual sections to get the optimal, or to get as close as it can to that KT/J combo that we provided it. But you can see that the pitch of this particular propeller that I put in is about 1.1, basically 1.01. Almost all the blades, except for the very root, all the blades are within 1% of a pitch, or pitch to diameter ratio of 1. So you can just take whatever's at the midsection and call it that. So it's about 1.02 is our pitch to diameter ratio for this problem. So that's about it. You're going to be using this for your homework, kind of essentially doing what I just spoke about. That's all.